This is a video about 10 GHz moon bounce. I don't have any personal experience of that, but I do have from 2-meter aurora, and those signals are similar in nature. They are broadened by Doppler effect to a bandwidth of maybe 300 Hz or half a gigahertz or something of that order. There is a recording I have uploaded on the internet. It's on my home page in the SDR data file library. So I click here, and it's this file. I right click on it and save target as, and I don't want it in my documents. I want it some easy way. So my computer and this partition, which we are now running on C:, and I create a folder, wavlib, to store this and save. So now it's going to be saved, and in the meantime I will set up Linrad. Click on that, and S for normal mode, and 1 for a small font, and process priority normal, that's 0, and size, that's in percent, that's N, and let's make it 98 by 87. And don't forget to save parameters, but I have to click on this window first to give it the focus, and then save by W. And now I exit for now, escape. Now download is complete. I have opened the text editor and typed in a line with the file name and then a second file name on the same line. That's where the Linrad parameters will be stored for this file. And I save it in the Linrad directory, save as, and we are already here, and as adwav. This makes it very convenient to run this file many times. It's not so convenient to have to point to the different files that are scattered over big directory structures. But of course this could be made in a different way. I will first listen to the recording in a conventional radio, so I use Spectravue and point to the recording where we have it and open it and start. And here is the signal. I can click on it. If you know CW, it's not very difficult to copy this. I start again and look for the very weak signal we have here. If you are a trained operator, you could have heard that that was WA6PY. But it's on the limit of what a well-trained operator can copy, I think. I will now start Linrad and set parameters that correspond to what I demonstrated with Spectravue. First I have to set up the hardware and select what is the input, that's A, and I don't want any hardware, so I put disable, that's Z, and then something for the output, B, with output audio, and 0, which is the motherboard sound card. X, and W. And then 2 is processing the first file in ADVAV, that's 2. And I will run it in normal CW mode, that's B. Repeat recording endlessly, yes, why not? Interpret as I and Q, yes. And do not invert the frequency scale, that's no. And then with Spectravue I had the FFT size of 4096. That's what we get here as well. But the bandwidth is given as 47 Hz in Spectravue, and here you can see the bandwidth is 93 Hz. So I have to change that to 50. And I use twice the size of the transform, that's because of the window applied here. And the window shape is not very critical, so I don't worry about that. I know that this recording has a fairly large amplitude, so I change from 2000 to 20. And then accept everything else as the default by pressing enter. And here is the screen. And this is the full frequency range. And I want to make the waterfall a little bit easier, that is more gain and lower here. Now Linrad is averaging. You can see the transform is the average of each waterfall line is the average of 21 transforms. To be comparable to Spectravue, I cannot do any averaging, so I have to change here first. The first average is in groups of 3. I click on it until it says 1. It means do not average at all. And then I say draw a line for each spectrum. No, draw a line for every second spectrum, because I have overlapping because of the window. This should be comparable to what we saw in Spectravue. I can now click on a signal, this one, the mouse wheel, and I can quite conventional now. It works like a standard transceiver. Better visibility is obtained if the waterfall is averaged. And I can average here and make it, let's say, 50 transforms. Means 50 lower. Then you can see the color is much more even, so I can increase the color gain here, let's say 3. Then I must change the color 0 point to, let's say, 15. And then we can very clearly see the signals. Maybe 15 was a little bit too much, I say 14. Just 1 decibels difference now, and you can see that that makes a big difference. Here is a digital transmission of some kind. But we can see there are no very weak CW signals here. We can see several dB below this signal, and nothing of that sort is visible. Now I will change the setup to use some of the more special things inside Linrad. I can make the window a Gaussian window, that's 8. This will give me a little bit more transforms because overlap will be greater. And that's good for the AFC that I'm going to enable. The storage time is 1 second now. I increase that to, let's say, 30 seconds. To have data stored for the automatic frequency control, and then enable. That's 1 here, and I go for the default parameters here, maybe a little bit more, 250 Hz. And hertz per minute. Well, this is enough. First mixer bandwidth reduction in powers of 2 is 5. I increase that to, let's say, 8 to get smaller transforms in the baseband. And I go for a Gaussian window in the baseband as well. So that is 8. And we need a longer storage time here also. That can be 30 seconds also. And enter. And I don't have to look at the entire spectrum, so I put the interesting signals here. I don't want the frequency control window. Oops. I can place it here. Or like that. And listen to something. Here we have this weak station. And now I need to optimize the AFC, automatic frequency control. It's a very weak signal, you can see here, maybe equal to the noise within its natural bandwidth. So So signal plus noise is 3 dB above the noise floor only. So averaging is needed. Now it's averaging over 61 transforms. I increase that to, let's say, 150, and then fit to those average is, let's say, 300 points as a straight line. You can see the red straight line that is fitted to the green points, which are the averages, and the resulting frequency that Linrad is using is the white line. I have to click. Then the signal comes here, and now I can reduce the bandwidth to fit the signal. And theory tells me that the window should look the same as the power spectrum of the signal. So I do it like this. Something like that. And to see better, I increase the gain scale. Something like that. So I click the signal when it begins. You see, it's not at the right spot automatically, but when I click it, and I can introduce the audio expander now when the bandwidth is matched to the signal. And wait for it to come back again. Maybe easier to hear if the pitch is made higher. I have to wait for the next transmission. And there is a big averaging. I make this now 1, so we can see what happens with the frequency over time. And to see, I need to put a 1 here as well. seems the filter is a little bit too narrow. I think it is not so difficult to copy here. And the significance of this exponentiation. Not very big, but I can make the effect larger. X, P, enter, 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 and exponent is 2, I make it 3, and here we are. Enable it. There was a Y, da di da da, da di da da. So the signal to noise ratio is not so low, it's 8 decibels or something like that. But it is in the matched filters bandwidth. This method works much better when the ratio of the modulation bandwidth and the Doppler spread bandwidth is bigger. So slower CW speed and worse Doppler spreading makes this procedure more useful. I click on a strong signal now. And now I will disable the AFC for this station. And you can see it is maybe 12 dB. So the difference is not that big, but are weak on EME. And here you can see this station and how the frequency changes over time. So one cannot listen to this one without the automatic frequency control and within a matched filter. And imagine that this would be the weak signal. That that would point to what is useful with this procedure. So I enable again the AFC to show one more thing about how it works. So I can disable the output by right-clicking, and then here it comes, so I click on it now. And we have a delay of 9 transforms. That was a mistake. It should be the biggest possible. Means that we take the frequency for the midpoint of this red line rather than doing an extrapolation. And what that means will be clear for the next repetition of this station. Well, I will click on this when it begins for the next transmission. I don't have a working video editor, so there are some periods of less interest in this video. I have used the YouTube editor to connect several short videos to do this. And as soon as I see it here, I will click on it. Here. And you heard the first CQ, because we have this delay of 157 transforms. Da da di da, da di da di da da di da. So we can read it visually also. I can expand that. But you can see the variations during the dashes is not much smaller than the distance from the noise floor to the average of the signal.